Hello, everyone. In this part, we will look into FIFO and min page replacement algorithms. So these are algorithms that operating system can use to select which page to evict. Okay. So before looking into those algorithms, let's look at few definitions that are used when while trying to explain various page replacement algorithms. Okay, and these are also few things that you may be asked if you go for any job interview related to operating systems companies, or in general these definitions are good to know. So the first is pressure. Pressure is just a demand for some resource. So for instance, when somebody says memory pressure, that means there is a high demand for memory. Eviction means throwing something out. Page eviction means uh, taking a page away from the physical memory and putting it onto the disk. That's called eviction. Pollution is bringing in useless pages or useless cache lines. Okay, for instance, bringing in useless pages into the main memory causes page pollution. Similarly, bringing useless memory into the cache causes cache pollutions. So by useless, here in this case, useless means they are not used by the process. So next, trashing. So trashing is extremely high rate of moving things around, usually like ping pong kind of situations. And most of the times, these situations are unnecessary. For instance, if we are repeatedly taking a page away and putting into the disk and bring the page back in, like in a ping pong fashion, that's called trashing. Okay, and most often trashing implies some inefficient decisions taken by the operating system. Okay, and ideally we don't want trashing to occur. Locality means reuse. So programs have this amazing property called locality. Okay, so most of the programs, as observed by Donald Knuth, like 90% of the time is spent by a program will be done on 10% of the code. So this gives this nice property of locality. That means program is just reusing most of the stuff, like either it's reusing the code or it's reusing data. And locality can be either temporal or spatial. Temporal locality is reuse in time. Temporal means time. So when we reuse in time, that means it's temporal locality. That means if we are using the same page again and again, that means the page has high temporal locality. Okay. Spatial locality is reuse in space. That means reusing uh, adjacent memory locations. For instance, if we say that a process has high space locality, that means, or high spatial locality, that means the probability of process accessing an adjacent page, like given a memory access, the probability of process accessing an adjacent memory is very high. That means it will have high spatial locality. So, and before understanding page replacement policies or page replacement algorithms, what is like, how can we compare the efficiency of page replacement algorithms? So one of the simple metric is any page replacement algorithm should minimize the number of page faults at the end, right? And this is similar to cache miss rate. Like if you have taken architecture course, this the this requirement is similar to cache misses. Okay, so if we want to decrease, like any page replacement policy should have minimal page faults. What about hit latency and miss latency, right? We also want them to be small as well. Uh, so we don't want a page replacement algorithm that minimizes page faults. However, every time we miss a page, or like every time a page fault occurs, imagine if it takes 5 minutes. That's undesirable, right? So even the latency should be less as well. So we have two requirements. We should have minimal page faults, and the latency when hit or miss occurs for a page, the latency should be very less. So what can we do without hardware support? Let's say we do not have any hardware support. What are the page replacement policies we can think of? Okay, our good old friend, first in, first out. Operating system can keep track of physical pages that are recently swapped in, and whenever a page is needed, it will just pick the oldest page, and that will be the page that will be evicted. Okay, so here in this case, you can see that it's a operating system maintains a queue of pages, okay, that have been evicted. Okay, so whenever a page is needed, it will go to the head of the queue and it will pick that page as the victim page, which needs to be evicted. Okay, and the implementation is has very low overhead because all it needs is to just access the page number. That's it. And disadvantage is that this algorithm doesn't consider recency. That means the page that is being evicted may be very frequently used by the process, right? So it doesn't care. We just take out the oldest page, although it is used frequently. So that is disadvantage. This can lead to trashing. So where every time, we let's say here in this case, if we need a page, we will pick page 15 as the victim page. We swap out and we swap in our required page. However, let's say 15, let's say the process requires that memory again, then we need to bring back the page again from the main memory and then put it back, right? So this can happen, especially if if process uses that page more frequently. However, in FIFO, we don't take care of that. That's one disadvantage. So another interesting property of FIFO is, let's say for a given set of page references or memory references, what happens when we increase the physical memory? Okay. Basically, let's say you are running two processes, okay, and you are using FIFO replacement policy, page replacement policy. Okay, what happens when you have like 1 GB of RAM? Okay, and what happens when you increase the RAM to 2 GB? So you expect the number of page faults to decrease, right? However, that's not the case. It's very interesting property of FIFO. So for a given, so to reiterate the problem, so let's say there are two processes running, you have some set of memory references. The number of page faults that happen when the memory is 1 GB, okay, will be less than number of page faults that happens when you increase the memory, that's 2 GB, right? So if you increase the memory, your performance could decrease if you use FIFO. So this is called Beledi's anomaly. Of course, Lazo Beledi is the person who identified this property, where the number of page faults actually could increase with the number of physical frames available. Okay. So let's look at an example. So consider these as our page requests. Okay. And so these are the page requests. These are like virtual page requests. Okay. By a process. And let's say there are 3 physical frames available. Okay. That means, let's say the memory is, if each frame size is 4 KB, let's say the physical memory available is 12 KB. Okay. Now, given that these are the page requests, like page requests for the virtual pages. So first, here in this figure, the numbers or the blocks in red indicates page faults. So when we get request for page 3, we get page fault because that's the first time we are seeing page 3. So since we have 3 free frames available, so we load page 3 into frame 1. Okay. And next access, when we get access to page 2, then we also have, we get a page fault because that's not in the memory. However, we have free frame, which is frame 2, we load into frame 2. Now next, when we get request to page 1, we load it to another free frame 3. Okay. Now the fourth page request, when we get request to page 0, since it is FIFO, the oldest page that we got is loaded into frame 1. So we select frame 1 and that leads to page fault. So we load page 0 to frame 1, so on and so forth. So in total, you can see there are 9 page faults. Let's try to simulate the same thing by increasing page frames to 4. So here the main memory available is 16 KB. Okay, here the main memory available is 12 KB, total page faults is 9. Here total memory available is 16 KB. However, page faults increased. They increased it to 10. So this is called Belladis anomaly. Okay. So more like empirically, this can be like, this is what we would expect, right? As we increase the number of frames along the x-axis, uh, where the y-axis is the number of page faults, we see this inverse logarithmic curve. We expect this to be the case, right? However, in FIFO, this is what happens. As we increase the frames, the page faults might actually increase and decrease. Okay. So this is not desirable, right? This is not what we want. Like when we increase the frames, we should have improved page fault performance, or rather we should always decrease the, we should always see a decrease in the page faults. So another ideal, like what is the ideal page fault, page replacement algorithm? So this is algorithm is called optimal or min, and this is created by Belladis. It's also called Belladis algorithm. So here the goal is simple: replace the page that won't be used for the longest time. So here, whenever we need to make a decision of which place to which page to replace, we always search for the page that won't be used for the longest time, and we replace that particular page. And the advantages of this policy is we can prove that the number of page faults are minimal. Okay. And the disadvantages is there is no implementation for this because it's hard to know which page will not be used for the longest time, right? So because you cannot predict the future, so it's hard for any algorithm to know whether certain page will be used in future or not. So because of this, this algorithm is only used for as an offline component to compare the performance. So whenever you implement a page replacement policy, you always compare with the optimal page replacement policy and then see how well you perform with the ideal page replacement policy. So this min algorithm, like, or optimal algorithm, serves as a good yardstick to compare page replacement policies. Okay, by the way, do you remember we also had similar policy in CPU scheduling algorithm? That's shortest job first, right? So there also we had the very nice guarantee that if you use shortest job first algorithm, turnaround time will be minimal. Average turnaround time will be minimal. Okay. However, there we cannot implement that because you cannot know the total time by each process beforehand. So similar to that, here we cannot know whether a page, like which page won't be used for the longest time. So that's why we cannot use optimal or min in reality. However, we can use past to predict future. Like based on the principle of locality, we can say that a page which is recently used is most likely to be used again. Similarly, a page that is frequently used is again most likely to be used again. So these two are nice features of locality, which we can use to say whether a page will be used or not, right? Because if we know that a page is recently used, then most likely it will be used again. Similarly, if a page is most frequently used, then we know that the page will be used again. So we can use these features to determine whether a page will be used for the longest time or not. Okay. Note that these are temporal locality features because there is no spatial locality here because we are just always replacing one page. right? So we are not considering adjacent pages. And the recency and frequency are properties in time domain. So that's why these are temporal locality features. Again, like why don't we use spatial locality? The reason is we always replace one page. So we don't replace multiple pages at a time. So that's why we don't use spatial locality. We only consider temporal locality. Because again, we want to know which page will not be used for the longest time. So it's a temporal feature. That's why we use temporal locality features here. Okay. So how can we identify like page recency and page frequency, right? It's very hard to do it in software because in order to do it, you can imagine we need to monitor each and every memory access and to see whether which page that memory access belongs to, and we need to record the page accesses and page frequency, right? So in order to make this more efficient, hardware hardware has nice support. The way hardware supports this is it provides a bit called reference bit in the page table entry. And this bit will be set whenever process accesses this page. That way we know that that way we know that the page is being used by the process or not. So yeah, this bit is as shown on the slide. So in a page table entry, it's shown in color blue. So there is a bit called accessed bit in the page table entry. So this will be set by the MMU whenever a process accesses this page. Okay, that way we know that whether a physical page is accessed or not. Now, using this accessed bit, we can actually improve our like FIFO algorithm. Okay, we can have FIFO with second chance. Here, it's same FIFO, but we make a minor change. The change is before replacing the oldest page, we check if the reference bit is 1. That means we check if the page is used by the process or not. If the reference bit is 1, we just take the page and bring it to the front of the queue. Okay. And we do that, we continue going back until we find a page where the reference bit is 0. Once we find the page that reference bit is 0, that is the page that we will replace. Okay. The advantages of this is, again, it's very efficient. And now we actually take care of frequency. So we don't replace a page that is that's frequently used by the process, right? And the disadvantage of this is, in worst case, we may actually go through the entire queue. Because imagine if all the pages are most frequently used, or if all the pages have reference bit 1, then we will end up iterating through every page in the queue, right? This might increase the latency of handling page fault, and this is not desired, especially in real-time systems where we want page faults to be serviced quickly. So in the next part, we'll look into more fancier page replacement policies. Okay? Thank you.